All right, welcome to the Chapter 2 and Chapter 3 review discussion. Post a couple of questions up here, so we'll go through these. But let's start with the very first one from Chapter 2, where we're given a piecewise function, and then we're asked a couple of things. We're asked to find out, say, f of, oh, they have f of -3. Right. So the function is defined on intervals, right? The interval where x is less than -2 is one function. When x is between 2 and 0, it's another function. Between 0 and 4 is a third function itself, and then another one, right? So when we look at this, we just really have to start by finding where this x value lies, right? This -3 is up here. It would be -3 is less than or equal to -2, so it fits this criteria. So I plug it into this piece of the function. And so this would be negative, x is -3 here, and then -5. Which is to say +3 minus 5, which is -2. So that's the big deal, is just figuring out where it's applicable to plug this into, and then plugging it into that right part, right? So I think it's probably going to ask f of -2. And so it doesn't work here because this is a strictly greater than. So x, if it's -2, is not strictly greater than -2, so it doesn't qualify here. We're still in this first piece. And so -2 is indeed less than or equal to, because it's equal to -2, so it goes into this piece as well. So that's -2 minus 5, or 2 minus 5, which is -3. And then I think they just keep moving on here, so like f of -1, well, we would plug that into here because it's now fitting this criteria, and so that would be -1 gets squared, and then -1, so that's 1 minus 1, which is 0. Right? F of 4 fits this criteria, right? And so we would plug it into this, so that is the square root of 4. X is 4, so that's 2. Right? And then anything beyond that, f of 5, f of 6, f of 7, would fit this criteria, and therefore you would plug it into this bottom one. So know how those piecewise functions work, because you'll likely see one on the test. We also, in Chapter 2, saw the difference quotients. This will become a big thing in calculus if you move on to calculus, and I assume that since you're in pre-calculus, you will go to calculus. But maybe not. But let's take this f of x. This is just the second problem, and I know these aren't numbered. I've always meant to go back and number them, but I didn't. But I have 4x squared plus 5. And it's asking us to find the difference quotient, f of a plus h, just make sure I get the notation right here, minus f of a all over h. Right. So for this function, it's convenient, in the homework we saw, it's convenient just to find out what f of a plus h is, find out what f of a is, and then take the difference. You don't really have to do that, you can do this all in one go. F of a plus h is just plugging a plus h in for the x value. So there's my f of a plus h. I'm going to subtract off the f of a, so in parentheses I'm going to put this 4x squared. And then that whole thing gets plopped over in h. So I want to expand this a plus h, right? This is, there's a 4 still. A plus h squared becomes a squared plus 2ah plus h squared. Expand that, just a plus h times a plus h. Foil it if you need to. Plus this 5. And then I'll just distribute this negative, because I can, so minus 4x squared, and then minus 5. Still all over h. I'm writing kind of big. I'm going to go back up. And I'll take this up to the top. But I'll distribute this 4 through, so that gives me 4a squared plus 8ah plus h squared plus 5 minus 4x squared and then minus 5. So they get long a little bit, but they cancel out a lot. 4a squared, my bad. This is not f of a, this is f of x, so this should be an a. Zoop. And this should be an a. Zoop. There we go. But the 4a squared and the minus 4a squared cancel out. Gone. Gone. The 5 and the negative 5 cancel out. And I'm only left with 2 terms. Right? 8ah plus h squared all over h. But my 2 terms in the top have an h that I can factor out. And so this is an h. Factored out leaves me with 8a plus h all over h. And now that this h is a factor in the numerator, it can cancel with a factor of the h in the denominator, and I'm just left with 8ah. Sorry, 8a plus h. So know how to go through that process, find the difference quotient, and then simplify it down to something that looks like this. And you should eventually end up canceling out that h in the denominator. All right. I don't know where my lid went to. I guess it doesn't matter. All right. Let's take a look at the second to last one. We're given 2 functions. I'm given f of x as 5x plus 8. And I'm given g of x as 1 over x. And we're asked to find a few things, f of g, f of a couple of different types of things. Let's just do a few of them. Let's look at f of g of x. That is f composed with g of x. Right? Now again, this just means take g and put it into f. So that is to say, you have f of g of x. Which is to say, I'm going to take 1 over x, right? This is f of 1 over x, which is to say, instead of the x in f, I'm going to replace it with 1 over x. So that is 5 times 1 over x plus 8. Right? Or you can simplify this if you like, write it as 5 over x plus 8. But that's our f composed of g. We can do the other way and take g composed of f. Which again is like just taking f of x and plugging it into g. So that is g of f of x, or if you like, that is to say this 5x plus 8 gets plugged into g, and therefore g, which is 1 over this, is now 1 over x becomes 1 over 5x plus 8. So this is then 1 over 5x plus 8. And there it is. Okay. You might be asked to find a specific value. So let's say, again with these 2 functions, you're asked to find in here f, let's go f of g of 5. And I'll do this 2 ways because you can do it both ways. Right? This I can say, let's find f of g of x, and then plug in 5 later. But again, that's just taking g and plugging it in here. So instead of the x, I have 5 times 1 over x plus 8 which we said you could simplify as 5 over x plus 8. And I want to evaluate this at 5, so now I plug in 5. So I have 5 over 5 plus 8. 5 over 5 is 1, plus 8 is 9. Right? Or you can figure out what g of 5 is. Right? G of 5 is 1 over 5. And so then f composed of g at 5 is f of 1 over 5. Because that's g composed of 5. And therefore this is just f 5 times 1 over 5 plus 8. You can see that 5 times 1 over 5 is still 1, plus 8 is then still 9. Right? So either way you think about it, you get the same result. Good. All right, and then the very last one, let's do this g of x. Oh, okay. G of x equals x minus 1 squared plus 3. And we're asked to find the inverse, right? So that's what we want to do, is find the inverse. So the first thing I would do is get rid of the g of x notation in favor of y. Swap my x's and y's, so this becomes x equals y minus 1 squared plus 3. And then solve for y. The easiest way to get this y alone is to get this term here alone, and I would subtract 3 to do that. So I'm going to pick out the easiest thing to do. That leaves me with x minus 3 is equal to y minus 1 squared. Alright. I can't really mess with what's inside the parentheses, but I can take a square root, right? So I take square root this, square root this. The square root kills the square on the right hand side. So I have the square root of x minus 3 is equal to y minus 1. And now I can mess with the inside. I just have to add 1 to both sides. And this gives me the square root of x minus 3. End the square root and then add 1. Don't add 1 into the square root. And that's equal to y. And I'm done. That's that. And that's chapter 2 in a nutshell, right? So hopefully we're comfortable with that. Let's move on to a couple of problems from chapter 3. Let's look at the very first question. They ask us to find the vertex. And then they give us a function. Let's look at the f of x function. X squared plus 8x plus 11. Okay. And again, there's two ways of doing, well, there's more than two ways, but here is two ways to do it. The first way is to just simply take negative b over 2a as your x value, and then evaluate negative b over 2a to find your y value, right? So we find the x value, we plug it back into f to find the y value. Well, this is a is 1, b is 8, and c is 11, so negative b over 2a is negative 8 over 2 times, there's a 1 here, so 1, it's negative 8 over 2, that's negative 4. Okay. So my vertex is negative 4, comma, whatever 4 plugged back into this function gives me. So f of negative 4 is negative 4 squared plus 8 times negative 4 plus 11. Negative 4 squared is 16. 8 times negative 4 is negative 32. And then plus 11. So negative 16 plus 11 is negative 5. And that's my vertex. And that's the first way of doing it. The second way of doing it is to complete the square, right? And that's not a bad method. I'll go through it now. Let's take a look at this. But I should end up with the same number, so unless I can't add or subtract, which is, it happens, but we should end up with this, right? So to complete the square, I don't want to mess with both sides. I really just want to play with one side. So I want the number, instead of an 11 here, I want that number to be the square of half of the middle, right? That is to say, take that middle number and half it, and then square it, right? Half of 8 is 4, squared is 16. So I want this to be a 16. So how do I get that to be a 16, right? Because I'm 5 off, but that's okay. I can add 5 and subtract 5 at the same time. That's adding 0, and then I'll just combine the 11 and the 5 to give me my 16, and that negative 5 is just going to hang off to the side. It shouldn't be a surprise that that's going to be a negative 5, because that's the y value of a vertex, right? But if I complete the square here, let me just write this as x squared plus 8x plus 16 minus 5. These three terms, if I group, are a perfect square trinomial. This is x plus 4 squared minus 5. And I've completed my square. The x value is the opposite of the number in here, so it's negative 4, and then the y value is the same sign as the number out here, negative 5. And so my vertex is negative 4, negative 5, which is what we got in the first one. We'll see a lot of this pop back up in pre-calc 2, you'll see it a lot. In calc, you'll see it come back. So know how to complete your squares, because you'll see them, they don't go away. Alright, let's look at the next one. We'll do one of these where it says to sketch the polynomial. So it says sketch by completely factoring finding the zeros under multiplicity, and the end behavior. Okay. So let's take one of these. We'll do the hard one, which looks like the last one, h of x. So h of x equals x to the 6th minus 2x to the 5th. Minus x to the 4th, plus 4x to the 3rd, minus x squared, minus 2x, plus 1. Actually, this one turns out to be not terribly the hardest one. G of x might be, because there's more options for the division. But we're already into it, so let's keep moving. So the possible rational zeros here, are the p's over q's. But this is why this one's not very hard, because p is either positive or negative 1, q is positive or negative 1. I don't have a lot of options here. It's either a plus 1 or a minus 1 divided by 1. I have two options here. It's those, right? So that's it, that's all I have here. So if I go through and do the division, I'm going to do a synthetic division. I'm going to go, I'll do this in perhaps a different color. 1, negative 2, negative 1, 4, negative 1, negative 2, and 1. I'm going to start with 1. I have a feeling it'll work. It's a 50-50 shot. It's less than 50-50, but it's a pretty good shot that it's going to work here. The 1 just drops down. 1 times 1 is 1, that's 1. Negative 2 and 1, negative 2 and positive 1 is negative 1. That's a negative 1, that's a negative 2, and a negative 2, that's a 2, and a 2, and a 1, and a 1, a negative 1, and a negative 1, and a 0, right? So it worked the first time, that's one of them. Probably going to work a second time, the 1 drops down, 1, 1, 1 is 1, that's a 0, that's a negative 2, so that's a negative 2, and that's a 0, and that's a 0, that's a 1, that's a 1, and that's a 0, so it worked a second time, right? Right? Try it again, because why not, right? Is this too low? No. 1 drops down, is that too low? Probably. The 1 drops down, we're trying 1 again, so 1 times 1 is 1, plus the 0 is 1, 1 times 1 is 1, plus the negative 2 is negative 1, so that gives me a negative 1, negative 1, negative 1, I get another 0 here. So in fact this 1 has worked 3 times, I've reduced myself down to a 3rd degree polynomial, I need the space, I'm going to carry this back up, so I know that I have 1 3 times. So I've got 1, 1, negative 1, negative 1, right? That's all I have left. And just because it's worked 3 times doesn't mean it's not going to work 4 times, so let's go with it. 1 again, the 1 drops down, 1 times 1 is 1, that gives me a 2, that gives me a 2, that is a 1, good lord, this is a whole bunch of 1s. So now there's 4 of them, right? So 4 of them, and this is a 2nd degree polynomial, and once I get to that point where I have a 2nd degree polynomial, I hate doing synthetic division, so screw this, I'm out. This is x squared plus 2x plus 1, right? But that's x plus 1 times x plus 1. So these are my negative ones, right? I have a positive 1 4 times, I have a negative 1 twice. And that's what I need, that's all I need, and really to get a rudimentary graph of this function. So let's see what this looks like. At 1, I have a 0, and at negative 1 I have a 0. And I know that these, the 0 at 1 has a multiplicity of 4, which is even, which means I'm going to touch, but not cross. And the same thing happens at negative 1 because there's 2 of those. Its multiplicity is even, therefore it's going to touch the line and then leave it, it's not going to cross through the line. The end behavior here depends on your leading coefficient. It's even and it's positive, and therefore I know my end behavior is that it'll go up as I go to the left or to the right, right? And so that's all I need to know, because if I come down here, I touch and I don't go through, and then I need to just come back down, touch and go through, and I have some W looking thing, and that's my graph, right? Again, I kind of feel bad about doing this one. I thought it was going to be the hard one. It is kind of the stupid one though. I can see a lot of people getting hung up with the number of 1s that you can divide out of here. But take a look at g of x, give that one a go, because there's a lot more possible zeros that you could pull out of that one. So there's positive or negative 1, 2, 4, 8, 16, or 32 on that one. But anyway, give it a shot. Let's look at one of the next question. Let's look at the middle one. This print is tiny, so I'm going to pull this up here. but we're asked to find the quotient and the remainder. And then they give us 3x to the fourth minus 12x to the third plus 3x squared minus 16x plus 8 all over x minus 4. Okay. And so because the denominator is a simple first degree polynomial, I can, if I choose to do so, I can do long division, or I can do a synthetic and just divide out of 4, right? So it doesn't matter in this case, but the other two, synthetic division is a poor choice. Because the other two, the one on the right of this one has x squared minus 4 in the denominator, and the other one has a 2x plus 3 in the denominator. So you would actually have to be dividing out a -3/2 and then figure out how the coefficients work with taking that 2 out. So I wouldn't do that. Let's do long division here just because it's probably the easiest way to do this. So rather than writing this all over, I'm going to cheat and just take that. Okay. And so the first thing I would do is take the very first term of the divisor and whatever this is. This very first term here divided by the first term here. So 3x to the fourth divided by x gives me 3x to the third. And then I take that 3x to the third times x is 3x to the fourth. 3x to the third times -4 is -12x to the third. And then remember that you're subtracting what you got here, so you need to change the signs. So this is now minus, and that's now a plus. And so 3x to the fourth minus 3x to the fourth is 0. 12x to the third and -12x to the third is also 0, and so just pull down the next couple of terms. 3x squared minus 16x plus 8. Take the first non-zero term on the left, 3x squared, and divide it by that first term again. 3x squared divided by x is 3x. It's positive, so it's plus here. That gives me plus 3x. And then multiply again. 3x times x is 3x squared. 3x times -4 is minus 12x. Change those signs again, so that's now minus, that's plus. 3x squared minus 3x squared is 0. You should always get this 0 for the first term. If you don't, you goofed up. -16x plus 12x is -4x, and then just drop down that plus 8. And go again. -4x divided by x is -4, so minus 4. Minus 4 times x is minus 4x. Minus 4 times minus 4 is a positive 16. Change your signs. So that becomes 0, minus 8. And that's my remainder because I could no longer divide it by that first term evenly. So the quotient is here, and the remainder is -8. Good. Okay, let's take a look at the next question here, g of x. It says find all of the possible rational zeros, but don't actually go through and find them. And I think it's just because it's a horrific exercise. And so I'm not even going to write the full g of x because it's big. It starts with 20x to the 8th, right? That's important. the blah, blah, blah in the middle in here isn't, right? Then it ends in plus 32, and that is important. But that's the only thing I care about is this first term and the last term. And the reason that it says find the possible rational zeros but don't actually figure out which ones they are is because this list is going to not be small. It's going to be a big ugly list. Because all of my p's are the positive or negative factors of 32, which are 1, 2, 4, 8, 16, and 32. All of my q's are all of the possible factors of 20. So that is 1, 2, 4, 5, 10, and 20 itself, right? And the list of all the possible ones are 1 over 1, and 1 over 2, and 1 over 4, and 1 over 5, and 1 over 10, and 1 over 20, and 2 over 1, and 2 over 2, and 2 over 4, and 2 over 5, and 2 over yada yada yada. So it's a big list, right? So if I write this P over Q is positive or negative. You can eliminate writing half of them by just throwing the positive or negative. And then it's all of these. 1 over 1 is 1, 2 over 1 is 2, 4 over 1 is 4, 8 over 1 is 8, 16 over 1, 32 over 1. Then all of these things over a 2. So 1 over 2, 2 over 2 is already here, so I'm not going to write it. 4 over 2 is already here, 8 over 2 is already here, right? 8 over 2 is 4. So the nice thing about this is a lot of the 2's and 4's are going to cancel out because they're already here. 8 over 2 is 4, it's already here. 16 over 2 is 8, it's already here. 32 over 2 is 16, it's already here, right? 4 over 1 is 4, it's there already. 4 over 2 is 2, 4 over 4 is 1. 4 over 5 is not there, so here we are, 4 over 5. I think I weirdly went out of order. I did. Yeah. 2 over 1 is there, 2 over 2, 2 over 4, but 2 over 5 is not there. So at any rate, I've barfed it up because I'm, I don't know, thinking about something else maybe. But it's all of those. It's 1 over 1, 1 over 2, 1 over 4, 1 over 5, blah, blah, blah. And then the 2's over everything, the 4's over everything, and so on and so on. So it's a big list. I'm going to stop now because I feel like I've already barfed it up, but that's how you do that beautiful little thing. Okay. And then we had complex numbers show up, right? The i's. So know that this I is defined to be the square root of -1, right? We said, well, this isn't real, but let's call it something, right? And it's kind of unfortunate that they chose the name imaginary. The I stands for imaginary, but most mathematicians will call it complex instead, even though the term imaginary is never going anywhere. Because it's not like some fake BS number that we just pulled out of our butts to make a problem work. I mean, that is what happened, but they have true application in physics, mechanics. They're all over math. So anyway, we've got this, and then we had some operations that we wanted to do. So let's take a look at, like, say there's a problem 3 plus 5i, and that gets multiplied by 3 minus 2i. And to multiply this, I'm just going to treat it like I'm foiling. So 3 times 3 gives me 9. 3 times minus 2i gives me negative 6i. 5i times 3 is 15i. And then 5i times negative 2i, I get 5 times negative 2 is negative 10. I times I is I squared. And I can combine my I terms, negative 6 and plus 15. Is 9i. And then this I squared on the outside there is negative 1, right? And so I have negative 10 times negative 1, that's a plus 10. And now I can combine these two because they're both real. And so I have 19 plus 9i, and that's my final answer. So know how to multiply those guys together and then simplify. And also know how to divide. So there's a 7 minus 2i divided by 3 plus 2i. And division in the complex world is defined by not doing the division. It's defined by multiplying by the conjugate. So 3 minus 2i and 3 minus 2i. Right? All I'm really looking to do is rationalize this denominator. Once I do that, I have my final answer. So for the numerator, we're going to FOIL this. So 7 times 3 is 21. 7 times negative 2i is negative 14i. Negative 2i times 3 is negative 6i. And then negative 2i times negative 2i is a plus 4i squared. We'll come back to that and simplify in a minute. My denominator, I FOIL as well. 3 times 3 is 9. 3 times negative 2i is negative 6i. 2i times 3 is plus 6i, and then 2i times negative 2i is negative 4i squared. The reason that I chose that 3 minus 2i in the denominator is the negative 6i and the plus 6i cancel out. There's no more i's in the denominator once I get rid of this I squared in favor of a negative 1. And so this turns into 21 minus 14i minus 6i is minus 20i. And then I have plus 4i squared, but again that I squared is a minus, so I can just call that minus 4 over 9. And then minus 4 times I squared, which is negative 1, becomes a plus 4. I can simplify the numerator, 21 minus 4. Still minus 20i. All over 9 plus 4, and I'm done, right? A lot of times they'll ask you to put it into a plus bi form, right? So if you're on a test that you're writing, which is not going to happen in this class because we are in the world's weirdest year, this would have been fine. If you're on a test, just break this up and call this 17 over 13 minus 20 over 13 I. Break each piece of this over 13 individually. A is your 17 over 13, B is negative 20 over 13, and that's in the a plus bi form. Good. Okay. Now we would also have seen some equations now that we couldn't solve until this moment. X squared minus 6x plus 10 equals 0. You can use the quadratic formula, you can complete the square, you can try to factor. Factoring is not great here because it's not going to work, right? We're looking for factors of 10, 1 and 10, 2 and 5, that's your options. And you're never going to get a negative 6 out of these guys, right? So if I go with the quadratic formula, that is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Right? I can do it this way. Or I can complete the square. So I'll do this one this way, I'll do the other one, just kidding, the other one doesn't work so much that way. I'll do this one both ways. B is 6, so b is negative 6, so negative b is positive 6. Plus or minus, b squared is negative 6, but squared, so that's a 36. Minus 4 times a, which is 1, times c, which is 10. All over 2 times a, which is 2 times 1, so 2. So this is to say 6 plus or minus the square root of 36 minus 40 all over 2. And 36 minus 40 is negative 4, right? Let me take this up here. Should plan out my writing a little better. For this, 6 plus or minus the square root of negative 4 all over 2, but the negative can come out of here, so I get 6 plus or minus that I times the square root of 4 over 2. The square root of 4 is 2, so this is 6 plus or minus 2i all over 2. When you have it in this form, don't just cancel the 6 with the 2. That 2 has to cancel with everything in the sum because it really has to cancel with something that can factor out. So think of it like this. I factor out a 2 from the bottom, leaving me a 3 plus or minus I over 2. The 2 as a factor can cancel with the 2, and I'm left with 3 plus or minus I, which is to say my two answers are 3 plus I and 3 minus I. Good. That's the quadratic equation way. If you want to complete the square, that's equally, probably easier, I would think, in this case. Let's find out. To complete the square, I have an equals. It's not a function, f of x equals this. I have this thing equals 0, so I can play with the other side. So I'm going to subtract 10 just to get this guy out of my way to start. That leaves me with x squared minus 6x, give yourself a space to work, and equals negative 10. The number that I want here is the square of half of this middle number. So half of this is negative 3, square it is 9. That's what I want here, plus 9, and I'll plus 9 to the other side. That way the left-hand side is a perfect square of x minus 3 squared. I have a squared number on the left equals a negative on the right. There's your indication that there's going to be a complex value here. If I square root both sides, the square root and the square cancel, leaving me with x minus 3. This is a plus or minus when I take that square root, but that is an I. And therefore when I add 3 to both sides, I get the same answer. 3 plus or minus I, in less work, I think. All right, and then there's one last problem here. Let's take a look at, I don't know, the ugly one, looks like H. So we're supposed to graph by finding the x and the y intercepts, vertical and horizontal asymptotes, and points where the graph crosses the horizontal asymptotes. Okay, so I'm going to do all of these things. The function that I've chosen here, this ugly one, is h of x. I feel like I'm going to need all of this board a few times. Is equal to something very small, x plus 2 squared, x minus 3 to the third, x plus 5, and then in the denominator I have an x squared, x minus 1 squared, x plus 8 to the third. Okay. So the first thing I want to do is find the zeros of this function, that is to find the x-intercepts, right? And the zeros happen when the numerator is 0, so that happens when x plus 2 is 0. So my zeros happen at negative 2. So I'm going to write this. I want my zeros and their multiplicity, because I'll use that information. This has a multiplicity of 2 because it's squared, right? So at negative 2 I have a multiplicity of 2. At positive 3, I have a multiplicity of 3. And at negative 5, I have a multiplicity of 1. Okay. So there's my zeros. The zeros of the numerator give me the x-intercepts, right? And I'm going to skip the y-intercept for now. I'm going to jump straight to vertical asymptotes because it's finding the zeros of the denominator, right? So vertical asymptote happens at 0, at 1, and at negative 8. It's also worth noting the multiplicity of these asymptotes. At 0, I have a multiplicity of 2. At negative 1, I have a multiplicity of 2, and then at 8, I have a multiplicity of 3. And the reason I'll note that is because the behavior around these asymptotes is similar to the behavior of my zeros. At a 0, an even multiplicity means I'm not going to go from negative to positive or from positive to negative. I'm going to just come down, touch, and then stay on the same side. And the same thing happens here. An even multiplicity at a vertical asymptote means that you're going to either go down to infinity on one side of it and come up from infinity on the other side, or do the same thing from above, right? But if it's an even, you're going to stay either positive together or negative together. But if it's odd, you're going to switch. Okay? So that tells me a bit about my function's behavior as well. So the y-intercept happens when x is equal to 0, but there isn't going to be a y-intercept because if x is 0, I have a vertical asymptote. So there is none, and therefore I don't have to worry about it. Is there a horizontal asymptote? Perhaps. And I find out by looking at the power of the numerator. So there's a 2 and a 3 and then a 1. So altogether I have 6, x to the 6 in the numerator if I were to expand it all the way out. But in the denominator I have 2, 2, and 3. That's 7. So in the denominator I have a greater power, and therefore my horizontal asymptote is y equals 0. Okay. Points of crossing the horizontal asymptote. I would plug in 0 in for this. Well, that happens at these zeros. We've already found that. So that's not more work for us. We already know this. We don't have to worry about it. All I have to do now is graph this thing. So I'm going to erase the function itself because I don't need that. I'm going to take this horizontal asymptote and get it out of my way. Oh, and the last thing is end behavior. Oh, just kidding, not end behavior, because we have a rational function. Okay, so I have some zeros. I have a 0 at negative 2. I have a 0 at 3. And a 0 at 5. I know my multiplicities here. It's 2 and then 3 and then 1. So here I'll just write in a little parentheses it's 2, and that means that I'm going to touch, right? Or if you want to write just a T. But at 3 I have a multiplicity of 3, and therefore I know I'm going to cross. And then at 5 I have a multiplicity of 1, so I know I'm going to cross. Right? I don't know if when I come and touch, I don't know if I'm going to come and touch from the bottom and then go back up, or if I'm going to come from the top and then go back up, or come from the bottom and go down, but it's one of those two. Let's get our asymptotes in there. I have a vertical asymptote at 0, so I'll just kind of write a dotted line right here. I have one at 1, so that's 1. And then one at negative 8. Let's just call this negative 8. And then I have my horizontal asymptote at y equals 0, right? Okay. So I've got all of that information down. Now I just need to kind of reason my way through this, right? And really, I just need maybe one spot, one value that I can plug into this function and figure out if it's positive or negative. And so I will. I'll grab something easy like, say, negative 1. right? And I erased my functions, which was dumb. But if I plug in fact, let's maybe plug in 2, just to keep it positive, into this function, so I have this h of 2 is 2 plus 2 squared times 2 minus 3 to the third times 2 plus 5 all over 2 squared, 2 minus 1 squared, and then 2 plus 8 to the third. Okay. Is that too far over? No, but it looks good. And I don't even care what this number is. I picked a number that was not on an asymptote and was not a 0, so I just picked some random number, really. I don't care what this value is. I just want to know if it's positive or negative, right? 2 plus 2 is positive, square it's still positive. 2 minus 3 is negative, cube it, it's still negative. And 2 plus 5 is positive, so a positive times a negative times a positive is negative in the numerator. 2 squared is positive, 2 minus 1 doesn't matter because I square it, so it's positive, and then 2 plus 8 is positive, so it's positive. So a positive divided by a negative divided by a positive is negative. That's all I care about. I don't care if it's -1 or -5 million. I don't really care about how beautiful this picture looks with my peaks and troughs. All I care is the general look for now. And it's negative. So I have some point here at 2 that this thing is right there, right? And that's all I need. That's all I need to know, and I can graph the rest of this. Because between here, I have to go up and touch 3, and I have to cross. And therefore, I know I do this. I have to come back down and touch 5 and cross. And so I know I do this. I can't keep going down forever because I have an asymptote here, so I get pulled back and eventually just approach that asymptote. Right? That's what I do there. This asymptote right here, I have 2 choices. I can either go up and follow up, or I can go down. It doesn't make sense to say it might go up, because if I went up, I would have to have a 0 somewhere between that asymptote and 3, and there aren't any. We found all of them, and there's not one here. So this guy, his only choice is to continue downward. Okay. Now, the multiplicity here, this is 1. 1, right? The multiplicity of my vertical asymptote is 2, which means I'm not going to switch signs when I jump over that asymptote, which means on this side I have to be negative. And therefore I know I'm doing something like this. Okay. I'm going to approach very quickly another asymptote, so I have 2 options. I either go up or down it. But if I go up it, I have to cross over and get a 0 somewhere between 0 and 1. And there are not any, so I don't do that. What I do is I come up for some distance, I don't know how far, I don't care, but I fall back down, and I fall down on the asymptote at x equals 0. Okay. But hey, look at that, x equals 0, the vertical asymptote has a multiplicity of 2, so when I jump on the other side of it, I still don't change signs, and therefore, on this asymptote, I rise from negative infinity. And I know I come up here and touch, and therefore I know I'm going to do something like this, not cross through, I just touch and go back. And then I have this other asymptote. Again, 2 options, I either go up, but if I go up, I should either have crossed here or have another 0 between that -2 and the 8. I don't, so I know I have to go down. Right? And then at -8, my multiplicity is 3, so I do change signs, so I don't come back up, I come from above, and then this would asymptotically then approach that horizontal asymptote. Again, that's the ugly one, and I don't know how long it took me because I wasn't paying attention, but something like this would be murder to put on a test, something this difficult. But the first two are fair game. So try to make it through the first two. This one was horrific because there was a lot to it, but because there was a lot to it, it was easy to explain my way through it. So try the other two, make sure that you understand how to put all of this together. If you have difficulty making those reasonings, instead of saying the multiplicity says I should be here or there, just evaluate some points into the original function, get a positive or negative, and figure out where you are at a bunch of points, and then essentially connect the dots. So hopefully that was helpful. This was one of the longer videos. We're at 55.5 minutes now, but hopefully it was helpful. Keep up the good work, and I will see you guys for the next one.